You probably know the formula for the volume of a sphere, 4/3 times pi times r cubed. In school, we're often just told to memorize this formula because its derivation isn't exactly straightforward. But this formula was already discovered in ancient Greece, long before the invention of calculus. So how did people back then figure it out? In this video, I'll show you the brilliant method Archimedes used. He combined math and physics in a surprisingly clever way. And once you see how he did it, you'll likely be amazed by the brilliance of ancient mathematicians. Before we begin the derivation, let's review some geometric results that were known in Archimedes' time. The area of a circle, pi times r squared. The volume of a cylinder, pi times r squared times h. The volume of a cone, 1/3 times pi times r squared times h. In addition, Archimedes had discovered the law of the lever. That is his famous saying, "Give me a place to stand, and I will move the earth." He also calculated the centers of mass for many geometric shapes, including spheres and cones. Let's start by drawing a circle with radius a. Its equation is x squared plus y squared equals a squared. Although coordinate systems and algebraic equations didn't exist in ancient Greece, I'll use them here to more clearly explain Archimedes' geometric reasoning. This equation essentially describes a curve where the relationship between the horizontal and vertical coordinates always satisfies the Pythagorean theorem. So using coordinates is simply a convenience. It doesn't change the geometric essence of Archimedes' thinking. Now we place the circle so that it's tangent to the y-axis. Its equation becomes x minus a squared plus y squared equals a squared. We consider the sphere as the shape generated by rotating the circle. Our goal is to manipulate this equation in a way that helps us relate it to the area of circles. Let's expand this equation. We get x squared minus 2ax plus a squared plus y squared equals a squared. And then simplify it. We get x squared plus y squared equals 2ax. Now multiply both sides by pi. We get pi x squared plus pi y squared equals pi times 2ax. So now pi x squared and pi y squared can be seen as areas of circles. But what exactly do these areas correspond to? Remember that xy represents the coordinates of a point on the circle, where x is the horizontal coordinate and y is the vertical coordinate. Let's first look at the vertical coordinate y. If we pick any position, then pi y squared represents the area of that circle. If this light yellow point moves along the circumference from the left side to the right side, then don't all of these circular areas together form the volume of the sphere? In other words, as the light yellow point moves from left to right, pi y squared can represent the cross-sectional area of the sphere at each position. But we still don't know the exact volume of the sphere. So let's keep this conclusion in mind for now. Now let's look at the first term in the equation, pi x squared. We continue letting this point move from the left side to the right side, and we get a series of circle areas. But do these circles form the volume of some geometric solid? We can't be certain, but we can think in another way. If we draw a straight line y equals x, then at each position, the x length equals the y direction length along that line. So the area pi x squared can be thought of as standing up vertically. Now look again at these circular areas as the point moves from left to right. What do they form? A straight line rotated around an axis forms a cone. In other words, as the light yellow point moves from the left side to the right side, more specifically, from the origin to the point 0, 2a, pi x squared can represent the cross-sectional area of this cone at each position. So far, we already know that pi x squared represents a cross-sectional area of the cone, and pi y squared represents a cross-sectional area of the sphere. But the meaning of the right-hand side is still unclear. The clever Archimedes then multiplied both sides by 2a, giving this equation. Now pi times 2a squared can also represent the area of a circle. It represents the area of a circle with radius 2a, and the diameter of this circle is exactly 2a. So if we take this line as the radius and rotate it around the x-axis once, the resulting circular area is exactly pi times 2a squared. Likewise, as our light yellow point moves along the circumference, at every position we can construct circles of the same size. Each of these circles has area pi times 2a squared. Eventually, these circles can be seen as the cross-sections of a cylinder. But what are the meanings of the 2a on the left and the x on the right? Archimedes then remembered his famous saying, "Give me a place to stand, and I can move the earth." He thought of the law of the lever. The 2a and x can represent lever arms, and these terms can represent weights. What does this mean? He took the coordinate origin as the fulcrum and constructed a balance. Then he hung the circle represented by pi y squared on the left side of the balance at a distance of 2a from the origin, and also hung the circle represented by pi x squared at the same position. On the right side of the balance, he placed the circle represented by pi times 2a squared at a position x units away from the origin. Now let's take another look at this equation. Isn't the left-hand side describing the torque on the left, that is, the weight multiplied by its lever arm? And isn't the right-hand side describing the torque on the right side of the balance? If we understand it this way, then the equal sign in the equation tells us that the balance is perfectly level. Note that the area or volume here can be treated as weight. You can imagine that their densities are all 1, so weight is directly proportional to volume or area. If we continue moving the light yellow point, then at every position we can hang them in the same way, and the equation ensures the balance is always in equilibrium. That means we can repeat this process for every point from 0 to 2a, suspending a pair of discs just like before. Since all individual positions are in balance, then their sum must also be balanced. That means if we hang the entire sphere and cone on the left side and place the cylinder on the right side, the balance must also be in equilibrium. From this balance relationship, we can get the following equation. The volume of the sphere plus the volume of the cone multiplied by the distance from their center of mass to the fulcrum, which is 2a, equals the volume of the cylinder multiplied by the distance from its center of mass to the fulcrum, which is a. And Archimedes already knew the volume formulas for the cone and the cylinder, so substituting them in. Simplify the equation, we get the volume of the sphere, 4/3 pi a cubed, where a is the radius. Looking back at this whole journey to discover the volume of a sphere, I can't help but feel amazed. You really have to admire Archimedes' intelligence and imagination. But at the same time, we realize something important. Even a shape as simple and elegant as a sphere takes a surprising amount of effort to analyze. If the shape were just a little more complicated, perhaps even Archimedes wouldn't have been able to solve it. And that's exactly where calculus comes in. It allows us to break down shapes into tiny pieces and add them up. It's a powerful tool that helps anyone, not just geniuses, tackle complex problems in a systematic way.